So, welcome to this class on cryptanalysis of classical ciphers. So, we will essentially be continuing with what we were discussing about classical ciphers and rather discuss about some cryptanalytic techniques or attacking methods or methods to find out the keys in context to classical ciphers. So, in today's class our objectives are as follows. We will discuss about certain models for which are used for cryptanalysis, which exist for cryptanalysis, and then essentially discuss about the cryptanalysis of monoalphabetic and polyalphabetic ciphers and conclude with cryptanalysis of Hill ciphers. So, to start with, as we were discussing that one of the fundamental principles in cryptography is or cryptanalysis is the Karskov's principle, which says that the crypto system is always available in the public domain, is known to the adversary, but what is not known is the value of the key. So, the entire secrecy of the crypto system lies in the key, and cryptanalysis is that field of cryptology which tries to obtain the value of the key, and it tries to find out the value of the key typically better than a brute force search. That rather than doing an exhaustive search, it tries to find out or develop methods or methods to find out or rather to obtain the key better than a brute force search of for the key. So, there are certain models which have been laid down for cryptanalysis, and these models are often useful for the study of ciphers. The first and the most obvious is a ciphertext only attack, where the opponent possesses a string of ciphertext, and that means that the opponent or the attacker has access to only the ciphertext or the crypto text. From there it tries to obtain the key. Now, this is the kind of attack which is probably we would expect in a real life scenario, and therefore it is kind of the sort of the strongest or the hardest task from the point of view of the attacker, which has only the information of the ciphertext. But in real life, or rather when we do our studies, we actually sometimes allow the attacker or the cryptanalyzer or the cryptanalyst some extra information apart from the ciphertext. What we do is that we sometimes, for example, we give an information of the plain text and try to say that, okay, you have the ciphertext and you also have the corresponding plain text, and from there you try to deduce the value of the key. Now, this may not be I mean intuitively very practical, but it is often very relevant, and there can be a lot of examples where these kind of attacks, which are known as the known plain text attacks or chosen plain text attacks, can be also practical. So, typically in a known plain text attack, the opponent possesses a plain text X and also the corresponding ciphertext Y. Now, in order to give you a practical scenario, imagine that is, for example, a case where we write an email and we respond to the email by generally pressing the reply button. So, what may happen is, for example, the text that I have written remains in your reply message. So, this is a typical example where for example, I know what is the content of the plain text, and if I observe the kind of network, then I also have an access to the corresponding ciphertext. So, this is an example of a known plain text attack where I have an access to a plain text and also I obtain the corresponding ciphertext. Now, also this becomes kind of more relevant in context to asymmetric ciphers, where anybody can encrypt, because as we were discussing that in an asymmetric cipher there are two keys, right? One of them is the public key and the other one is the private key. So in this case, everybody who knows the public key, right? The public key is known to everybody. So which means that everybody can or anybody can encrypt a plain text message, and therefore to obtain the ciphertext for a corresponding plain text is not a difficult job. So therefore you can have ample amount of tuples for plain text and ciphertext. So therefore in such kind of conditions, known plain text attack is kind of not very non-intuitive or not very impractical, and therefore it is also used as an important model for studying. Okay, so there are some other models for cryptanalysis also, like the chosen plain text attack, where the attacker can choose plain text and obtain the corresponding ciphertext. So in this case, the attacker does not only know the plain text, but can also choose the plain text. Okay, so this is an extra power or extra capability which is there in the adversary. As you can understand, all these are actually different levels of adversary, right? So which one is the kind of strongest attacker? The chosen plain text attacker is stronger than a known plain text attacker, which is stronger than a ciphertext only attacker, right? So in terms of information, the ciphertext only attacker has got the least information compared to the known plaintext attacker, and which has even a lesser information compared to the chosen plaintext attacker. So there is another important model which is also used, which is known as the chosen ciphertext. So in this case, the opponent has got a temporary access to also the decryption function. What he can do is that he can choose ciphertext and decrypt to obtain the corresponding plaintexts. Okay, but what is to be kept in mind is that in this case of chosen ciphertext, the idea is like this, that is, an attacker is given a large number of ciphertext, and also using its decryption function it obtains its corresponding plaintext. But in this decryption function, the key is kind of embedded. So therefore, when we are doing the decryption function, then the attacker does not have the knowledge of the key, right? But at the end of this kind of operation, which we call as oracle queries, what is done is that the attacker is given a challenge ciphertext and is asked to find out the corresponding key. Okay, so this comes at the end of all the previous exchanges which has taken place. So in this case, the attacker is kind of a strongest, right? So this notion is kind of a strongest notion, which has gotten access to not only the encryption function, but also can do decryption functions of a significant number of corresponding ciphertexts, right? So therefore, in this case, in each case, the objective is to obtain the key, and we can say that in increasing order of strength, the ciphertext only attacker is the least strong attacker. Then comes the known plaintext attack, then comes the chosen plaintext attack, and finally the chosen ciphertext attack, which is the strongest form of the attacker. Okay, so when you are designing a cipher, then ideally you would like to kind of look into the chosen ciphertext attack and kind of say that, okay, my crypto system is prevented or protective against as a strong form of attack as such as that of the chosen ciphertext attack, right? So therefore, ideally I would like to kind of counter even the chosen ciphertext attack. And from the point of view, when you are kind of attacking systems, right, when you are doing research in cryptanalysis, then you would be more happy if you are able to find out a ciphertext only attack, and you are kind of less happy as you go down the series, right? So because that attack becomes less and less stronger or more weak. Okay, so now we will kind of discuss some tools which are often used for cryptanalysis, but it may be kept in mind that these techniques are mainly applicable to ciphers which are old, that is the classical ciphers. Okay, the machine ciphers or the modern ciphers are much more robust, are much more strong. Okay, so to start with, let us make some observations. Like we see that English language, for example, has got certain probabilities of occurrences. Okay, so therefore typically we have got 26 letters, and there are certain statistics which you can easily observe if you kind of do analysis over a large number of texts. For example, E has got the highest probability and occurs with a probability of around 12%. The next in order comes these letters, these alphabets like T, A, O, I, N, S, H, and R. Okay, and T and L comes around 0.04, and there are some other letters like as mentioned here like C, U, M, W, F, G, Y, P, and B, which comes between around 0.015 and 0.028, and then we have got V, K, J, X, Q, and Z, which are less than 0.01. So these are kind of single occurrences of letters. If you kind of observe diagrams or double occurrences of letters, then TH is supposedly the most commonly occurring diagram. Then you have got HE, then you have got IN, and you have got these diagrams in decreasing order. Similarly, common trigrams would be like THE is the highest occurring trigram, and then you have got this particular series. So you can actually form statistics, and we call these statistics as a priori statistics before you start the cryptanalysis. Okay, so therefore this is the knowledge of the plaintext that you have. Okay, so you know that, and a person who is using a cipher is trying to do an encryption over a meaningful message, right? So this meaningful message is in our case assumed to be formed of English language. Okay, English language characters. It belongs to the English language grammar. Okay, and therefore what we have done is, for example, these statistics are of some English language texts that have been pre-processed, and from there people have found out frequency distributions of single occurrences, of double occurrences, triple occurrences, and so on. Okay, and this is actually a very useful information when you are doing cryptanalysis. So to start with, let us consider a shift cipher. If you remember, in a shift cipher, which we studied in context to monoalphabetic ciphers, then every letter is kind of given a shift, right? So therefore, for example, E, which is the most commonly occurring letter, is also shifted, right? So in case of Caesar cipher, you know, it has been shifted by say 3 steps, okay? So E becomes F, G and H, right? So therefore, if E was the most commonly occurring letter in normal plain text, then in the cipher text which uses the Caesar cipher, for example, then H would be the most commonly occurring letter, right? So therefore, if you observe, if you take a kind of piece of cryptogram or the cipher text and you start finding out the letter which occurs most frequently, and suppose the letter is H, right? So in that case, you can kind of conclude that H has got correspondence with E in the normal letter, right? So that is the way how you can actually obtain the shift which exists in case of shift cipher. So that is what we have said here. So in case of, so this is actually an example of a cipher text only attack, because you are using only the letter frequencies, because you are having an access only to the cipher text, okay? The other information which you have got is the letter frequencies in the English language, or that is the plain text and plain text character sets. So these are the kind of some frequency distributions. You can see that E is the most commonly occurring letter, okay? Similarly, you have got T, A, O, I and so on. So this is the gradual frequency bar to show the frequency distribution. So in context of an affine cipher, you see that suppose an attacker, so let us consider a little bit, let us consider the affine cipher. You remember the affine cipher, right? So suppose an attacker has got the following cipher from an affine cipher. So this is the kind of cipher text which has been kind of retrieved by an attacker, and he knows that the cipher which is being correspondingly used is the affine cipher. So let us try to do some cryptanalysis. So first of all, we try to find out the frequency of occurrences of the letters, okay? So if we find out, for example, that R has got an occurrence of 8, D has an occurrence of 7, E and H and K has an occurrence of 5, F, S and V has an occurrence of 4, okay? So first of all, we will try to guess the letters and solve the equations, and then decrypt the cipher and judge whether it makes any meaningful sentence or not. So the first guess would be like R, as I told you that R is the highest occurring letter, and therefore it should correspond to E, because as we have studied in this frequency diagram, that E is generally the most frequently available letter, is the most frequently occurring letter. So in the cipher text, if R is the most commonly occurring letter, then we know that since it's an affine cipher, then R should have corresponded to E. So therefore we make a mapping like R is E, and similarly the next occurring letter is in this case D, okay? So the next occurring letter in this case being D, we say that okay, D must correspond to the next occurring letter which is T, okay? So we say that D must have been mapped from T. So therefore we can actually write these equations. We know that EK, so if I encode E as 4 and R is as 17, so all the alphabets are being encoded by numbers from 0 to 25. So similarly we have got the other equation as EK on 19, and we know that that is equal to 3. So D is 3 and 19 denotes T. So then we have got these equations. So if you remember that in affine ciphers you have two keys. The key was kind of a tuple A comma B, and therefore you can write equations like 4A plus B is equal to 17 and 19A plus B is equal to 3. So therefore if you solve this, you will find that A is equal to 6 and B is equal to 19. So immediately you can say that this is a wrong guess. Why? Because if you remember, in affine cipher it is a requirement, because of the invertibility of the affine cipher, that A has to be co-prime to 26. So if you take a greatest common divisor of A and 26, you should get 1. But since this number is 6, and you know that if you take a GCD with 26, you actually get 2, and since this is not equal to 1, so this is an incorrect decipherment. So therefore we go for the next guess. So keeping R as E, what we do is that we take the next occurring letter, which is in this case E, okay, and we say that okay, let E mapped to T. So in this case you get A is equal to 13, and 13 is again not correct, because 13 and 26, the GCD will be 13, which is not equal to 1. So then we go for the next occurrence. Therefore then we again keep R as E, and the next occurring letter is H, which is mapped, so T is mapped to H, and therefore if you solve now, again you get A is equal to 18, which is again not correct because of the same reason, that is the GCD of A and 26 is again not equal to 1. So we can continue like this. So luckily for us, the next guess is correct, and we say that okay, let T get mapped to K. So therefore you see that the next occurring letters, so we take as T, has got mapped into the next occurring letter, which is k in this case, and therefore we say that t has got mapped into k, and therefore the corresponding equation is in this case. We solve this and we get a is equal to 3 and b is equal to 5. So we now think that this is correct, because if I take the GCD of a and 26, then I indeed get 1, and therefore I say that okay, the formula can be this, that is 3x plus 5 mod 26, which is the encryption of x when k is used as the key. So the corresponding decryption function is actually obtained as 9y minus 19 mod 26, and this decryption function exists because GCD of a and 26 was equal to 1. So this we have discussed in the last class. So using this decryption function, we can actually decrypt the entire cipher text, and we get that algorithms are quite general definition so far, and you get kind of a meaningful text. And therefore, if the decrypt if this decrypted text wouldn't have been meaningful, then we would have tried another guess. So therefore, you see that this is a kind of technique, and therefore it can be programmed where you can actually compute the frequency and solve the equations and check whether the GCD of a and 26 was equal to 1. So in this case, in case of affine ciphers, you know that the total number of possible keys is 12 into 26, which is equal to 312 keys, which is quite small, and therefore you can indeed write a program to try all the keys. Okay, but you know that so therefore the idea behind affine cipher is that you can actually use the frequency analysis technique quite efficiently. That is, you can actually form an a priori kind of frequency distribution of the English language text. From the English language text, you can form an a priori frequency distribution of the characters, of the alphabets, of the diagrams and the trigrams, and you can actually use this information to obtain the corresponding decipherment of the output of an affine cipher. Okay, but this may not be so obvious when you are actually having a polyalphabetic cipher, because in a polyalphabetic cipher, one particular alphabet, if you remember, can get mapped into various alphabets, right? And therefore the frequency distribution is not exactly maintained in this fashion. Okay, but you can actually discuss, and we will be discussing and see that actually you can use this idea, but you have to use it in a little bit more clever way. Okay, so let us study that next. So therefore we discussed the cryptanalysis of the polyalphabetic cipher. Example of that we discussed was the Vineyard cipher. So in some sense, the cryptanalysis of Vineyard cipher is also a systematic method and can be totally programmed. But first of all, let us try to understand that in a case of a polyalphabetic cipher, if you remember that you have to actually obtain the key first, right? So therefore the first step is to determine the length of the key. Okay, so what is done in a polyalphabetic cipher, if you just to recap, you remember that you have got this plain text message. So let us just consider a plain text message. So for example, this is a class on cryptanalysis. Okay, and the key could be, for example, code. Okay, so in a case of a polyalphabetic cipher, what we did was we took this code, this keyword code, and we kind of repeated them, right? So therefore we kept like this, and we performed an addition operation. So the rest was a normal shift cipher. So we took t, we added with the corresponding number with c and took a modulo and obtained this. So the point which we noted here is that this t, because of its different occurrences, right, could be actually transformed by either c or o or with d or with e. So therefore every letter, like if I take t for example, can be shifted by c, can be shifted by o, can be shifted by d, can be shifted by e. So if you have got a keyword like this, which has got, instead of 4 length, has got a length of m, then every letter has, if there is a possibility, can be encoded in a possibly by m possible transformations, right? So therefore the first interesting or the first important step is to determine the length of this key, that is to find out that how many ways can letter get mapped. Okay, so for this we do a study, and the first step is known as the Kaczynski step. So therefore the first step is to determine the length m of the word. It's called Kaczynski test, and then we will confirm them by a term which is called as the index of coincidence. So we will first of all try to determine this key, that is k is equal to k1, k2, and so therefore first of all we will find out the length of the key, and then in the second step we will determine the key. Okay, and we will determine each of these key quite separately, that is independently of each other. So the first observation is that if there are two identical plain text segments, then they will be encrypted to the same ciphertext when they appear delta positions apart in the plain text, where delta is actually congruent to 0 modulo p, modulo m. So this actually holds vice versa. So therefore the idea is that if there are two identical plain text segments, say for example there are two identical plain text segments, and they will be encrypted to the same ciphertext whenever they appear a multiple of m number of times apart in the plain text. Okay, see for example if there is a particular letter like THE, so this is an example of a trigram, and this is being, so therefore if there is a repetition of this plain text somewhere, like if the THE occurs again somewhere, and in the ciphertext also we have got a kind of, suppose you just take any corresponding ciphertext, like suppose this is mapped by ABC, then you can actually say that the separation of this and this, that is this separation is actually a multiple of the size of the key, because the key has to exactly kind of divide this, the size of the key has to exactly divide this separation. Okay, so therefore if this occurs here, that is if there is an identical kind of plain text segment and it also encrypts to the same ciphertext, then we can actually say that their separation, so if we measure the separation of these two texts, then this distance is actually a multiple of the size of the key. So you can actually take the ciphertext, and from there you can find out similar such occurrences, and you can actually start observing the distances, and because the size of the key actually divides all these distances, so then what you can do is that you can actually find out the greatest common divisor of the distances, and that can actually serve as a key size. Okay, so that can serve as your key size. So what you can do is that you can very well say that the key size is actually a so therefore it actually divides all these distances, and therefore it must divide the greatest common divisor of these distances. Okay, and then in a later test, which is known as the index of coincidence test, we kind of confirm this test. We kind of confirm this key size. So therefore, what we do is that we take the ciphertext and we search them for pairs of identical segments, and then we record the distances between them, between their starting positions. So suppose they are delta 1, delta 2 and so on, then m should divide all of these delta i's, and therefore m should divide the GCD of all these delta i's. Okay, so this can be used. So in the next text what we do is that we actually use the index of coincidence to determine m, as well as to we use it to confirm the m, which is determined by the Kaczynski test. So what is the definition of the index of coincidence? So let us see the definition. Okay, so suppose your x is equal to x1 to x1, x2 and so on till xn. So this is a string of length n, right? Now the index of coincidence of x, okay, is denoted, so it is often denoted by ICX, and it is defined to be the probability that two random elements of x are identical. Okay, so you take an x which is a string and you find out the index of coincidence, and it is defined to be the probability that if you take two random elements of x, then they are identical. So let us try to compute this index of coincidence, and let us assume that the frequencies of a, b and so on till z in x is actually obtained to be f0, f1 and so on till f25. So now we will try to find out that what is the probability that two random elements of x are identical. Okay, so how many ways can you actually choose randomly two elements from this string of length n? You can actually choose them by NC2 ways, and since you want to find out the probability that two random elements of x are actually identical, so which means that if the first letter which you have chosen is a, then the second letter is also a. Okay, if the first letter is b, then the second letter is also b. So if we assume that the frequency of occurrence of a is denoted by f0, then how many ways can you choose? Can both the choosings, right? Both the when you are choosing both times, then both times you are choosing A. So how many ways can you do that? It is actually, if the first time if you have chosen this f0 times, right, in the second case it can be like the remaining f0 minus 1 cases, because the first case you have already chosen this. So that means that if you kind of make a sigma over this, then that means that so if you have got A occurrences, okay, so that is, if you have got what I am trying to say is this, that is there are n letters, so you have got x1 to xn, and that forms your string x, okay, and you know that the occurrence of A here is denoted by f0, the occurrence of B is denoted by f1, similarly the occurrence of Z is denoted by f25, okay. So how many ways can you choose two elements? It is n choose 2, okay. And how many ways can both the letters be A? So that is the question, right? You have to determine the probability, you have to find out the probability that two random elements of X are identical. This is what you have to find out, okay. So you see that the number of cases where you have got A is actually denoted by f0. So therefore if you have got to choose two letters from here, both of them are A, it is actually f0 choose 2, because you have to choose these two letters from these f0a's, right. The second thing, you can actually choose them by f1 choose 2, because that gives you the number of ways in which you can choose B, okay. So you can continue like this, and the final thing will be f25 choose 2. So you can actually approximate this, and this will be actually equal to sigma, this is actually equal to sigma fi into fi minus 1 divided by n into n minus 1, okay, for all possible i's. So this you can actually approximate and make it equal to sigma fi square by n square. You can actually bring this n square below, and you can actually neglect this minus 1, okay. So this actually will work out to be equal to sigma pi square, okay. So that is the square of the probability. So you can actually deduce this in this fashion, and therefore you obtain this result, that is the index of coincidence is nothing but sigma fi into fi minus 1 divided by n square. So you can actually neglect this minus 1 from both sides, and then you can actually divide fi and make it fi by n, and that is squared. So therefore fi by n is nothing but the probability that the ith letter occurs. So therefore you get sigma pi square, which is denoted by here as sigma pi square. So that means that you obtain the probability of any alphabet and then find out the square, and then you take a sigma of over all the possible I values, okay. So this you can actually do here. So therefore suppose X is an English text denoted by the expected probability of occurrences of A, B and Z and so on till A, B and so on till Z, and then the frequencies are denoted by P0, P1 and so on till P25 with values from the frequency graph as we have seen before. Then the probabilities of two random elements, both of them being A, is P0 squared, both of them being B is P1 squared, and therefore you can say that the ICX as we have seen before is sigma pi squared, and therefore if you take the squares like 0.082 square plus 0.015 square plus so on, you get a value of 0.065. Now this value is very important because of a reason that if I'll tell you exactly why it is important, but please remember this number. So it is 0.065, okay. So now if y is the cipher text which is obtained by a shift cipher, then what is ICY? So that is the question, okay. So if I take x and if I kind of transform this x by a shift cipher, then what will be the ICY? So you note one thing, that if you take a shift cipher, then every alphabet set is kind of just permuted, right? The frequency distributions as such do not get changed. So therefore the ICYX actually do not get changed, and it should remain 0.065 because the individual probabilities will be just permuted, okay. But the sigma pi square will not change, that will remain invariant. So this property is actually used or exploited to determine the key value. So we continue with our index of coincidence, and then what we do is that, so if you remember that in our Kaspersky test we have got a suggestion of m, right? So what we do is that starting from 1 to m, we actually start arranging this entire letters like this. So you have got like y1, y2 and so on till yn, which is the cipher text which is obtained from the polyalphabetic Vineyard cipher. Then for any given m, if we are to kind of confirm this value of m, what we do is that we start dividing y into m substrings like this. So what we do is that we make m substrings like y1, y2 and so on till ym like this. So we have got y1 first, then y2 and so on till ym, then ym plus 1, ym plus 2 and so on till y2m. Then we have got start from y2m plus 1, y2m plus 2 and so on till y3m, and we continue like this. Okay. So if m is indeed the keyword length, then you see that each of these rows, okay, each of these rows will essentially be a shift cipher, right? Because if you remember how the polyalphabetic cipher works, so if your keyword is actually indeed indeed a string of length m, then each of these letters are actually being obtained from the plain text by shifting them by suppose this is by the first alphabet in the key, this is shifted by the second alphabet in the key, and so on. This is shifted by the mth alphabet in the key. But what about this? This is again shifted by the first alphabet in the key, right? So therefore all these elements which are there in the rows, or all the cipher alphabets, right, are actually shifted by the same letter. So this is also shifted by the same letter, these are shifted by the same letters, and these are also shifted by the same letters. So which means that each of these rows are nothing but shift ciphers, and therefore their individual ICIs should also be equal to the should also be equal to 0.065. But if it is not so, then that is if m is not the actual keyword, then all of them will be a kind of a random string, because this will be shifted by something, this will be shifted by something, this will be, the next one will be shifted by something, right? So therefore they will serve as a kind of a random string. And therefore for a random string, actually you will find that if each of these alphabet occurs with a probability, each of these English language alphabets occurs with a probability of 1 by 26, then the IC of that corresponding text will be equal to 26 into 1 by 26 squared, because that is the sigma pi square in that case, and that works out to 0.038. Now you see that the 0.038 value and the 0.065 are actually quite distinguishable, right? So therefore you see that this is a property which exists in this character set, which is actually quite distinct from that of a random string. And therefore this, and as I told you at the very beginning of our classes, that if we have actually observed a property which makes, which kind of distinguishes the given cipher from a random distribution, then you can actually exploit that for developing an attack, which is precisely what is done here also. Okay, so therefore, first of all, in order to confirm the value of the keys of the key size, then what you do is that you start arranging them like this, and then you start finding out the ICs of the corresponding rows. If your ICs worked out to be 0.065 for all these rows, then the value of m is confirmed. Otherwise, if the value of ICs works out to around 0.038, then the value of m is a wrong value. Okay, so you can start with the next value until and unless m. So for the purpose of, in order to verify the keyword length m, what you do is that divide the cipher text into m substrings, and then you compute the index of coincidence for each substring. If all the IC values of the substrings are around 0.065, then m is the correct keyword length. Otherwise, m is not the correct keyword length. Okay. So if you want to use IC to determine the correct keyword length m, then what will you do? You start from beginning from m equal to 2, 3 and so on until an m, for which all the substrings have IC values of around 0.065. Now the question is how to determine the actual key, or the, so now you have got, or rather you have confirmed the size of the key. Now your objective is to find out each of these keys. Okay. So for doing that, or rather in order to determine the keyword, we use another concept which is known as the mutual index of coincidence. So mutual index of coincidence works as follows. So consider two strings like x and y, which are formed of x1, x2 and so on till xn, and y is formed of y1, y2 and so on till yn. These are strings of n and n dash alphabetic characters respectively. Then the mutual index of coincidence of x and y is denoted as this, MIC x comma y, and it is the probability that a random element of x is actually equal to the random element of y. So therefore, using the calculation is exactly the same as that of index of coincidence. If your probabilities of occurrences in case of A, B and so on, so it's actually not the probabilities but the frequencies. The frequencies are like f0, f1 until so on till f25, and for the next one it's f0 dash, f1 dash and so on till f25 dash. Then the mutual index of coincidence is obtained approximately as sigma fi, is obtained as sigma fi dash divided by n into n dash. So this n into n dash is nothing but the total number of ways in which you can choose two alphabets, and this is the total number of ways in which you can actually choose, so that both the things which you choose are the same, right? That is, both of them are either A or both of them are B and both of them are C and so on. So number of ways in which you can choose the ith letter from X from the first string is so that both of them are the same letters is fi, and the number of ways in which you can choose the ith element in the second string is fi dash, because that is the frequency of occurrences, and therefore the probability of the probability that a random element of X is equal to the random element of Y is given by this ratio. So if you see that if you have got A, B and so on till Z, and these are the corresponding probabilities like P0, P1 until so on to P25, and if Ki is used as the key, then each of these letters get transformed as A plus Ki, B gets transformed to B plus Ki and so on till Z gets transformed by Z plus Ki. So now if I ask you, like, what is the probability that in the cryptogram a character is A? So A is denoted by the letter 0, right, by the number 0. So therefore it is the probability corresponding to J plus Ki, which is equal to 0, and therefore J will be equal to minus Ki mod 26, that is, this probability will be equal to P minus Kj, right. So therefore that is equal to P of minus K, P of minus Ki. So that is Pj, which is P of minus Ki. So that is the corresponding probability. So what I am saying is basically that now if I tell you that what is the probability that in the cryptogram a character is A, then this is not A, right, it is actually A plus Ki. So therefore among all these strings, among all these alphabets, you have to find out which one corresponds to 0. So suppose J plus Ki corresponds to 0, therefore the corresponding probability here will be Pj, right, and this Pj is nothing but P of minus Ki. So similarly the probability that both characters in X and Y are A is therefore found out by P of minus Ki multiplied by P of minus Kj, because of their independent choosings, and similarly the probability that both characters in X and Y are B you can obtain by P1 minus Ki multiplied by P1 minus Kj, and you can continue in this fashion, and therefore the mutual index of coincidence of these two strings will be equal to sigma Ph minus Ki multiplied by Ph minus Kj, where h varies from 0 to 25, and that is equal to sigma h is equal to 0 to 25, and you can actually make some changes in the variables, and you will get that Ph multiplied by Ph plus Ki minus Kj, and then you take a sigma from h is equal to 0 to h equal to 25. Okay, so therefore you can actually obtain the mutual index of coincidence, and this value, therefore this mutual index of coincidence actually relies upon Ki minus Kj. So that is the shift, right. So therefore it depends upon the difference Ki minus Kj mod 26, and you can actually prove this, take it as an exercise, that a relative shift of I yields the same estimate as that of 26 minus I. That's quite trivial from this formula, right. So now you see that there are some typical values of mutual index of coincidence for different values of Ki minus Kj. So you see that if Ki minus Kj is 0, then it is same as that of the index of coincidence, and therefore you get a value of 0.065. But for other values of Ki minus Kj, you actually get a value which actually varies around 0.03, and therefore it is quite distinct from this fact that Ki minus Kj is equal to 0. So what you can do is that you can always fix a yi, and you can modify the corresponding yj by subtracting from 1 to 25, and then the value to which we get an MIC which is close to 0.065 will actually indicate the correct value of Ki minus Kj. So you can actually try to understand using this, that is, so if you want to compute the shift between two keys, what you do is that under the key Ki you obtain that this is the corresponding frequency of occurrences, and if under the corresponding key Kj, this is the frequency of occurrences, and you consider the MI between these two series and it works out to 0.065, then you can say that Ki minus Kj is equal to 0. right. That is observed from this table, that is if ki minus kj is 0, then this mutual index of coincidence is 0.065. But what if not? If it is not equal to so, then what you do is that you shift this, keep the first one same, that is keep the one of the frequencies same, but you start shifting the next one, okay. So you just start shifting them with say plus g like this, and therefore all of these frequencies, so therefore the frequency of a character being I is now f dash I minus g. So this is because of exactly the same thing which I told you in context to the which I told you previously. So therefore the corresponding frequency is f dash I minus g, and thus we compute the mutual index of coincidence of x and y g as sigma fi multiplied by with fi minus g dash divided by n dash. And now if we have got a value of 0.065 or close to it, then you can say that ki is equal to kj plus g. So therefore ki becomes equal to kj plus g, and from there you can actually compute the difference of ki minus kj being equal to g. So therefore you keep one of them constant and then keep on shifting the other values, then you can also start computing the mutual index of coincidence in this fashion. And then if this mutual index of coincidence matches to 0.065, then you can say that okay, this particular shift is actually the correct shift, and ki and kj are actually having a difference of this shift which is equal to g in this case. So I'll give you some examples to show how it works. So this is an example to show this is an example of a cipher text. The first important thing is to obtain the kind of common occurrences. So you see that this CHR is a trigram which occurs at certain distances. It occurs kind of repeats, right? And we observe that the text CHR starts at 1, 166, 236 and 286 positions, and therefore the distances between the first occurrences and the successive ones are 165, 235 and 285. So if you know that if I take a GCD of these different distances, then it works out to 5, and therefore we verify m by computing the IC by trying m is equal to 1, 2, 3, 4 and 5. Okay, so we like to verify this m by the index of coincidence test. So what we do first of all is that we kind of take one of these rows. So therefore this is the one of the rows. So we have actually divided them and we have formed. So what we do is that we start forming 5 rows, and the first row is given as this. Okay, so this is the first row. So what we do is that we actually form an index of coincidence. So we again obtain the corresponding frequencies, and after obtaining the frequencies we obtain the IC value. So if we obtain this IC value, this value comes around 0.065, and this actually holds for all the other 4 rows also. So therefore if the m is anything other than 5, then as we have discussed, then the ICX would have been around 0.04. Okay, but since you are getting a 0.065 value, then the value of m equal to 5 is actually confirmed by this text. So next thing is to obtain the key. So how do you obtain the key? So now there are 313 characters in the text. It is divided into 5 rows because 5 is the length of the key, each having 62 characters, the last row having the remaining. Now each row of the table has been shifted as we have discussed by the same key. So its index of coincidence was 0.06. So we have actually observed that. Now we need to obtain, or rather compute, the shifts by the mutual index of coincidence text. So what we do is that we actually form each of these rows, and for each of these rows we actually assume that an English language text would have been shifted by a 0. So in that case ki was equal to 0, and we try to find out for every character, or rather for every row, what is the shift. For every row, what is the shift? Okay, so if you have got 5 rows, okay, so if you have got row 1, row 2 and so on till row 5, then we assume that this row 1 is shifted by the first letter in the key, which is k1. The second one is being shifted by k2, and so on. This one is being shifted by km, right? So the first objective is to find out what is k1 minus k0. Okay, so what is the value of k1 minus k0? So what is k0 in this case? K0 is 0, because that corresponds to the normal English language text. So similarly we find out k2 minus 0 and so on till km minus 0 to obtain the corresponding values of the key. Okay, so therefore we have obtained the frequency distributions here. We know the frequency distributions in context of the normal English language. So we kind of compute the mutual index of coincidence between this string and a normal English language string. Okay, so that kind of gives us an estimate of ki minus 0, k1 minus 0. So we can actually automate this process, and using that automation we have actually we can actually obtain the key and decrypt it. Okay. So I will give you another example. So this is an example of another ciphertext. In this case also you see that we obtain the commonly occurring strings, and this is the first index and the second index. The difference is denoted here, and therefore the Kaspersky test does predict that the key size will be the GCD, which is in this case 4. So if you take a GCD of these things, you get to 4. Okay. So we will confirm this text. So therefore we again break it into 4 rows in this case. So the first string is this, second string is this, third string is this, and fourth string is this. So we actually obtain quite high values, more than 0.06, and therefore the size of the key is confirmed. Okay. So then we would need to compute the shift of each row. So what we do is that we perform the mutual index of coincidence to obtain the actual key value. So we run this test, that is we find out we have got the English language. So we have got the corresponding we obtain the corresponding frequency distribution of this string, and we also know the frequency distribution, which is the a priori frequency distribution in English language. We use these two frequencies to compute the mutual index of coincidence of this string, and actually the corresponding value for which we get 0.065 is actually the correct string. Okay. So therefore we actually obtain the is the actual value of the key, that is we obtain the shift. Okay. So what we do is that we assume that the shift in this case is 0. We assume that the shift in this case is 1, then and so on till the shift is 25. Whichever shift actually gives us the mutual index of value to be 0.065 is the correct shift. Okay. And that we do exactly as this, that is like this. Okay. So if this is not, then we actually start varying this g from 0 to 25, from 1 to 25, and whichever value actually gives the value of 0.065 is the correct estimate. So that is the way of obtaining the corresponding key bit or the key value, key alphabet, right. So in this case we perform this, and the corresponding if you run this test, we have actually automated this, and you can obtain this key value is in this case code, and the corresponding plain text is this. Okay. And it makes a meaningful text, and therefore we conclude that our decryption has been correct. So then we actually discuss and conclude with the cryptanalysis of Hill cipher. So in this case the ciphertext only attack is difficult because there is a large key space. The key space is actually for an m cross m matrix. It can be as high as 26 to the power of m square, but actually it will be not so high because all the matrices are not invertible, right. But in a Hill cipher it is important that the matrix also has to be invertible. So the Hill ciphers, but there is a point, is that there is an important point to be stressed, that is Hill ciphers do not preserve the statistics of the plain text, and therefore frequency analysis does not work. Now for a key matrix of size m cross m, a frequency analysis of size m may work, but it is very rare for the plain text to have strings of the same character. So I mean it may work for a size of m, but it is very rare for a plain text to have strings of same characters of size m, because m is quite large. Okay. So for example THE can occur again frequently. Okay. CA, but the probability of a kind of trigram to repeat is more than a kind of a string which has got say 10 letters which has to repeat. Okay. The probability reduces. So therefore if you have got a letter, I mean if the value of m is suppose something like 50, then a probability that in your text this particular string of length 50 will repeat is quite small. So therefore you will get very small samples, okay, to work with, and since this is a statistical technique, this may not work. Okay. So therefore I mean a plain and simple analysis, a plain and simple ciphertext only attack like what we have seen previously may not work. However, a known plain text attack can easily work. Okay. Like, so in this case you see that if you can actually create two m cross m matrices, one for the plain text and one for the ciphertext, and if the key matrix is k is denoted by k, then you can actually represent it by C is equal to P into K, and here every row of the C and the P are corresponding ciphertext and plain text pairs, and therefore you can actually obtain the K if this plain text matrix is invertible as simply as multiplying P inverse with C. So here is an example which says that assume that m is equal to 3 and some known plain text ciphertext pairs are given here, like suppose 05, 07, 10 is getting mapped into 03, 06, 00, 13, 17, 07 is getting mapped to 14, 16 and 09, 00, 05 and 04 is getting mapped to 03, 1 7 and 1 1. So you can actually form two matrices, plain text and ciphertext matrices, and use them to obtain the inverse of the matrix P. And actually in this case P is luckily invertible. If P is not invertible, then you have to actually obtain more plain text ciphertext pairs, okay, and find out which one is invertible. And from there you can actually obtain the corresponding key K by multiplying P inverse with C. So this is quite straightforward and can be done. And the other so essentially this gives us a technique of doing a or mounting a known plain text attack on the standard Hill cipher. So I will give you certain points to think on, like why does a Hill cipher at all disturb the frequency of the plain text. So you can take a Hill cipher of size m and you can try to kind of find out why essentially the frequency of the plain text is disturbed, okay. The other important thing which you can try to do is that you can write a C program to automate the cryptanalysis of polyalphabetic ciphers, and you can try to play around with various ciphers, okay. Like you can take a normal English text and you can kind of encrypt using a linear cipher, a polyalphabetic cipher, choose some key values and obtain the ciphertext, and then you give it rather feed it to your program and see whether you are able to retrieve the key. If you are able to retrieve the size of the key, the actual key, and from there you are actually able to decipher the ciphertext, okay. And the interesting thing of this test is that it can be automated. So therefore you can actually write a nice program and play around and experiment with them. So the reference that I followed is Cryptography and Network Security, the second edition of the book, and by Farozan and myself. And next day we shall actually continue with Shannon's theory.